Hello! This is the sections 4.1 through 4.3 video prep work, and we're going to go through some of this really quickly. We'll do like a little intro to each of the topics. First one is the Bernoulli distribution. Shout out Bernoullis. Anyway, simplest possible kind of experiment that you could ever think of, because it is this experiment where there's one trial resulting in a success or failure, just like a yes or no. It's like a switch. It's either this or that. All right? And our random variable just counts the number of successes. I don't know why that does that. All right? So x is either 0 or 1. And the probability that x is 1 is just the probability of success. All right, so x is actually counting the number of successes, and if it's a 1, you have a success. So this is like with probability p, little p. So little p is literally reserved for this. And then this is the probability of a failure, so that's going to be probability 1 minus p. All right, so that's really what you need to know about Bernoulli. It's just something that's 0 or 1, and it counts the number of successes, and the number of successes have a probability, okay? The thing that's interesting about these is that when you start combining a bunch of these, you get kind of interesting things to happen, and once in a while you need to combine a bunch of these, as we'll see in the next section. So suppose the probability that a random student attends class today is like 90%, 0.9. X equals 1 if Mike attends, otherwise it's x equals 0, and y equals 0 if Axel attends, otherwise it's y equals 0. Sorry about that. All right, so what is this is p sub x, p sub y. This is just the probability of success for x. For Mike, probability of success is 90%. We're going to say if these are like independent kinds of things, right, then the probability for each of them would be like 0.9. So it's such a simple experiment, we just assume they're kind of identical. What does x plus y mean? And is it a Bernoulli random variable? So let's look at, if we're going to look at x plus y, I would make like a little table to look at it. So x can be 0 or 1, y can be 0 and 1. If we add those, right, we'll get a little table like this. If we added them, right, 0 plus 0 is 0, 0 plus 1 is 1, and so on. The question is, first of all, what does it mean, and is it a Bernoulli random variable? Well, x plus y can take values 0, 1, or 2, so no, it's not a Bernoulli random variable. No. Right? But does it have meaning? Yes. It's like the number of people who attend out of those two people, right? So it is meaningful. All right? And is there like a single probability of success for x plus y? No, because it's not Bernoulli. All right, but what if we wanted to do x times y? Well, if we want to do x times y, we can make a new table where, we multiply them instead, right? So if we're doing times 0 times 0, 0 times 1, 0 times 1, 0 times 1, 1 times 1. Well, now x times y, right, is 0 or 1. Looks like it's Bernoulli. Could we find the probability of this 1? Probably, right? Is it a Bernoulli random variable? Like, what does x times y mean? Well, it looks like it means like they both show up, right? Like if they both show up, it's a success, right? So x times y is right, it's 0, it's 1 if both show up, and 0 if not. And we could figure out the probability that they both show up. So you'll have something like that for a homework problem that you can try. All right, let's go on to 4.2, the binomial distribution. By the way, the binomial distribution is built of Bernoulli random variables, as you'll see in a second when we do our example. But the binomial, if you've already done the summary, you'll see the binomial probability function is based on this thing, the number of successes in n independent trials. All right, so it's actually like if you had several things, like 2 people, right? It's the number of successes out of those 2, or the number of successes out of 10, or whatever, okay? So out of n. Notice if you had n different Bernoulli trials, right, then x could take the value, number of successes could be 0, 1, 2, or it could be all of them are successes, n. All right, now we're going to look at this, the probability of getting one of those values. This is the probability mass function right here. Notice it's not given as a table, even though this is a discrete random variable. It's given as a formula. It has a specific mean. Okay, so this is the mean for this random variable, and this is the variance. So if you're going to take the standard deviation, be the square root of that. All right. The other thing they do here is we start talking about this idea of uncertainty, which is a statistical idea, which is always the standard deviation divided by the number in a sample. Okay, so if n was the number in a sample, but you might just see a couple homework problems like that. So I just wanted to make a note of that. But let's just look at kind of why this formula, why this PMF up here, why this works. Okay. So this guy, Giannis, plays for the Milwaukee Bucks. Giannis Antetokounmpo. I don't know how to say it. Antetokounmpo. There you go. Antetokounmpo. Makes 55% of his free throws. He's a basketball player. It's not very good. Not as bad as Shaq was. If he shoots 6 free throws, what is the probability he makes none of them? So you guys could make a little table, right? He succeeds or he fails, right? He succeeds or he fails on the second, and so on, right? Right? And you could figure out that the probability he makes none of them, well, if he makes 55%, then the probability P is 0.55, probability of success. So 1 minus P is 0.45. So the probability he makes no free throws would be 0.45 to the 6th power, right? So that would be like following down like this trail. Failure, 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 right? It's an and. Similarly, what's the probability he makes all of his free throws? Well, then that would be going off the top, this top one, right? So, oh, my pen's not working. Right? So 0.55 to the 6th. All right. Well, what's the probability he only makes the 5th and the 6th? Only the 5th and 6th. That means he misses 4 times, then he makes the 5th and the 6th. Well, that would be misses 4 times in a row. You could think about which trail that would be. Failure, 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 right? And then he makes the last 2. So whatever that is. Okay? So I'm not doing the calculations right now. But what's the probability he makes exactly 2 of them? Well, notice this is 2 of them, right? Only the 5th and the 6th, that's 2 of them. But what if it was the 1st and 2nd? That could also happen. Or the 3rd and the 5th. Or the 1st and the 6th, right? Notice there's lots of ways that exactly 2 happens. So this is where we get into the binomial idea. So we know that like the probabilities are going to end up being, there's 4 failures, right? And 2 successes. Like no matter which route you go down to get 2 successes, the probabilities will end up adding up that way. But how many are there? Right? How many ways can we have exactly 2? We could start counting them, right? Oh, the 1st and the 2nd, the 1st and the 3rd, the 1st and the 4th, right? But that's what we've been studying. How do you count those? We are picking out of 6 choices, we're picking 2 of them. 6 choose 2, right? So there will be, that's 15. 6 choose 2 different routes, 15 different routes in this big tree diagram that will give you exactly 2 failures. So at most 2 would be x equals 0, right? Or probability x equals 1 plus the probability x equals 2. So notice we can ask the question in some different ways. Now this would be 3 of these kinds of things, right? And we could do this one 2. Well, we did x equals 0. Which one was that? 0 successes. That was none of them. That was this one. So this would be 0.45 to the 6th. I don't know about this one in the middle. The x equals 2 we just did. Exactly 2 was this one. Well, you can kind of figure out what the other one's going to be, right? We know it's one success, 0.55 to the 1st, and you know the others are failures, so that's to the 5th, right? So notice these have to add up to 6, just like 4 and 2 added up to 6, but there's got to be 6 choose 1 places where that success happens. Okay, so notice it's not that hard to get, and what I want you to notice is that these are exactly of that form of the formula in the binomial formula that you have up there. What assumptions did we make to do this problem? Well, the assumptions we made is that he's not affected by, like, you know, he can fail 3 times in a row, and then next time the probability of success is still 55%, right? That is called independence, right? That his failure or success on a single trial, right, of the shots, his failure or success on a single trial is not affected by the failure or success on a previous trial. Okay, so that's called independence. Let's go back and look at those conditions for a binomial distribution real fast. Okay, so notice x is the number of successes in n independent trials, right? And notice here n factorial over x factorial, n minus x factorial, that's n choose x. This is p to the x, number of successes to the power, or probability of success to the number of successes power, and 1 minus p to n minus x, and this is the number of failures. And notice these will add up to n. Okay, those are the main things I want you to notice. We're going to go on and just look at 4.3 in a second. Okay, so this is 4.3, which is a third distribution, okay? It's called the Poisson distribution. I think that means fish in French. I don't know why it's called that. Maybe I'll look that up before we go to class. But what we have, this is a little different, okay? And I'm going to write it a little different than the book writes it, okay? So you'll see there's a lot of similarities in the way what the book has and what I have, but you'll see that I try to make really a ton of sense. But what we have here is the Poisson process, or Poisson experiment is always counting the number of events, all right, events, in a given continuous interval 0 to t. So you have like a time interval or a space interval or something like that. This interval is usually time or space related. So it could be like an acre of land in an acre of land, or in a 1 mile distance on a highway, or it could be in a 3-minute period, okay, like a time interval. All right, so what we're trying to see is like the number of times something happens in a given amount of time or space, okay? What we have to have is that the number of events are independent in non-overlapping intervals, and that the probability of having more than one in a really small interval has to be 0, okay? But what we need to know for this is we need to know the average number of events in a unit interval, or they also call it the rate of events per unit. All right, and then we're given this formula. It's harder to explain, but we know y is the number of events. So we know there could be 0 events. There could be 1 event. There could be 2 events. 3. Now, is there a top number of events we could have in a certain interval? Well, I mean, the probability will probably get reduced, but no, this could go on forever. Okay, so that's another formula we'll be using in class. All right, that's all I have. Bye-bye.